Next, let's take a coloring of an equilateral triangle example. For example, an equilateral triangle has 3 vertices, and now we can paint it using red, blue, green colors. How many possible different solutions are there? And then for now, let's be more sophisticated. For example, I would like to ask the corresponding 3 beads are all red in color. How many solutions are there? 2 red and 1 green. How many solutions are there? 1 green, 1 red, 1 blue. How many solutions are there? We may just use general function method to solve it. For its permutation group, it's actually very simple. It is just about rotation, positive and negative 120 degrees, and flipping around its symmetry axis, and no rotation. In total, there are 6 different permutations. This is the order over there. We need to find the corresponding generating function structure form. We saw there is a 1-3 order cycle. And this time, its corresponding generating function means that 3 inside the bracket should be selected the same color. Then its generating function is r to the power of 3 plus b to the power of 3 plus g to the power of 3, where for 1 order cycle there is 1, 2 order cycle, 1. By pulling this kind of format, it was written as a r plus b plus g multiplied by r squared plus b squared plus g squared. 1 order cycle, 3 2 order cycles. This actually is a r plus b plus g to the power of 3. If we take this equation and combine them all together, find the coefficient in front of several components, it's a corresponding solution number. For example, what we wish to ask is all about how many different types of red beans are there, which is during the expansion process. The coefficient in front of r to the power of 3. Then let's take a look at r to the power of 3. It is acceptable under which component? For example, r plus b plus g over the first row. Over here, we will realize there is 1 r to the power of 3, whereas in front, due to that there are 2, therefore 2 multiplied by the corresponding coefficient should be sufficient. Below this component, r plus b plus g multiplied by r squared plus b squared plus g squared, actually it will produce r to the power of 3 in total. How many this kind of permutation are there? 3. For the block, b plus r plus g to the power of 3 contains also r to the power of 3. We accumulate all this up together, we realize it is exactly 2 plus 3 plus 1. And same time, do not forget inside Polya theorem, we still need to divide it by the number of permutation. The permutation is 6. Therefore, it can calculate out 2 plus 3 plus 1 divided by 6 is equal to 1. Means that over a triangle, all the vertices are picking red, there is only one solution. Similarly, it will be calculating others. For example, we are what are the coefficients for RGB? Of course, we do not need to expand all the equations. We just need to look at each component will do. Over the first component, the corresponding should be r to the power of 3 plus b to the power of 3 plus g to the power of 3. It is not possible over here. RGB exists over there. Let's take a look at the second component. Inside the second component, each component is at least the quadratic component. Because in front it is r plus b plus g, the back is r squared plus b squared plus g squared. Therefore, it is not possible to appear RGB. By performing accumulated multiplication this way, only the last component inside r plus b plus g to the power of 3 may contain RGB component. But how many components are there? Actually, we all know that it may be 3 factorial divided by how many of r factorial, g 1 factorial. For this kind of repeatable permutation. Similarly, do not forget to divide by the factorial of 6. The answer is still our corresponding the possibility for RGB. The answer is still 1. Similarly, we can still calculate 2 beads, 1 blue beads, which is the same corresponding the first component. All other components are of the power of 3. Therefore, it's not possible to have a r squared b. Only over the second component we can get a b from the first component. The second component get r squared produced 1, where in total there are 3 different permutations. Therefore, for the second row, there are 2 corresponding r squared b appears. For r plus b plus g to the power of 3, we can also find the coefficient of r squared b. Actually, it is a result of repeatable permutations. It can be considered as using 3 factorial divided by r corresponding to repeatable permutation of 2r divided by 2 factorial, then divided by 1 factorial. Similarly, divide with 6 to get the corresponding answer. Let's look at if there's 4 beads need to be sealed on a hexahedron, how many different solutions are there? We can think carefully about it. How many vertices are there over a regular hexahedron? We will thinking that it should be 8 vertices. How many solutions? My suggestion that we have 4 beads, 4 red beads need to be sealed on top of 8 vertices, which means that some may be empty. Although there is only one color, but corresponding to the shading of red beads and the no shading red beads, there are two types of corresponding to coloring problem. And this time we directly perform two color coloring from hexagon vertices to perform the counting will be sufficient. But what is looking for over the last solution, the red beads must be 4. We use the L to represent R beads, use B to represent does not contain beads. Actually, we are just finding R to the power of 4, B to the power of 4. What is the coefficient in from it? And this time we are still using the same generating function type of Polya theorem. First, we could take the regular hexagon and list all the corresponding permutation, analyze it under a fixed situation. Vertices permutation should be 8 vertices. Each vertex is 1 order cycle. Therefore, it is a 1 order cycle to the power of 8. For face center to face center, the upper 4 vertices and the bottom 4 vertices form an exchanging. Therefore, 4 order cycle, there are 2. And following the same way down, we can list out all the permutation group of the vertices. What we are looking for is R to the power of 4, B to the power of 4. We can take the first component. R to the power of 4, B to the power of 4, the first component. If we write it into a generating function form, there are 8 1 order cycle, means that generating function is B plus R to the power of 8 will naturally exist B to the power of 4 and R to the power of 4. The corresponding coefficient in front should be pick 4 from the 8 component should be C8 4. For the face center to the face center rotation, there are 2 4 order cycles. Then if it was written into generating function, it will be B to the power of 4 plus the quadratic component of R to the power of 4. There may still contain the corresponding B to the power of 4, R to the power of 4. By following the same way down, analyze each component one by one. If it exists B to the power of 4, R to the power of 4, we can write out the corresponding generating function form. We can analyze the corresponding expansion format. B to the power of 4, the coefficient of R to the power of 4 should be equal to C8 4. Add up with 12, add up with 9 times C4 2, then add up with 8 times C1 2, multiplied by C1 2. Similarly, do not forget that we may still need to divide by the permutation number. For the regular hexagon, its permutation number is exact 24. Therefore, after covalent addition divided by 24, the answer is 7. What does it mean? It simply means that there is 4 vertices contain beads over a regular hexagon, where the remaining 4 vertices contain no beads. Under this kind of circumstance, different solutions are only 7 types.